Here we are in example 10. Once again, we're going to put to use everything we've learned in these first three sections of chapter 3, all in one problem. The first thing I'm going to do is find the x and y intercepts and the asymptotes. So once again, I'm going to pause the video here. I encourage you to pause and try to find those yourself too, and then you'll see them show up on the screen here in just a second. Okay, here's the important stuff that we gleaned from this information. There is no x-intercept because there's no way to get e to a power equal to 0. The y-intercept is what you get when you plug in 0 for x. That is a 1. And then when we're thinking about the limits, we know there's potential for a horizontal asymptote. We know there's potential for a different horizontal asymptote in both directions. But this one happens to have the horizontal asymptote equal to 0 in both directions. And I think it's easier to see that if we look at the function like this instead of with a negative exponent. So you can see it doesn't matter if you plug in a very big positive number or a very big negative number. Since the first thing we do is square the x, then that means we have e to a very large power in the denominator no matter what. It doesn't matter if we plugged in a positive or a negative. And so that means in both directions, as we go to infinity or negative infinity, the horizontal asymptote is going to be 0. So that's important, both directions. And we've got no vertical asymptotes because there's really nothing that would make this undefined. We're allowed to plug in any value for x and we'll be able to evaluate it. And there's no slant asymptotes because slant asymptotes only happen in these very specific instances where the numerator is 1 degree higher than the denominator, and that's really just not ever going to apply with exponential stuff like this. Okay, the next thing we want to look at, according to that box up above, is the derivatives and the domain. We've already kind of talked about the domain is all real numbers, and so there's nothing that we really have to watch out for as far as like finding critical points that actually aren't there. So let's find the first and second derivatives. We know that the derivative of an exponential function is itself, but then the chain rule says now we have to take the derivative of that exponent, so that's going to be a negative 2x. So I'm just going to rearrange that a little bit and write this first derivative as negative 2x times e to the negative x squared. Now in order to find a second derivative, I'm going to have to use a product rule. So we're going to say that's u, that's v. And as it turns out, v is the exact same function we had to begin with, so we already know what v prime is. It's the same as g prime. That's kind of the weird thing that happens with exponentials here. So if we put this together with the product rule, here's what it'll look like. And then just to make this a little easier to deal with later, I want to factor out this e to the negative x squared. And then we'll be left with, actually, let's go ahead and factor out a 2 also. Then we'll be left with 2x squared minus 1. So there's our second derivative. First derivative, second derivative. And then if we look back at that box strategy for sketching graphs above, we need critical values, and then we're going to find where it's increasing and decreasing and what the relative extrema are. So critical values happen when the first derivative is 0 or undefined. So there's my first derivative. I need it to be 0. We've already kind of talked about how there's nothing that's going to make this undefined because you're allowed to plug in any number for x in that situation. So we basically want to know what makes this part of it equal to 0 or what makes this part of it equal to 0, since it's already factored for us. So negative 2x equals 0 means x equals 0. If e to the negative x squared equals 0, that doesn't have a solution because there is no power that you can raise e to and get a 0. So again, just one critical value. I want to use the second derivative test to figure out if that critical value is a max or a min. So second derivative test, we're going to say, what's the second derivative at 0? It's going to be 2e to the 0 power times 2 times 0 squared minus 1. So this is 2 times 1 times negative 1, negative 2. So that means I got a negative answer, and so therefore we have a max at x equals 0. Specifically at 0, 1, because I already know the y value that goes along with x equals 0 because I found it over here when I was looking for intercepts. So that's my next very important bit of information. And so that tells me that if I'm looking at a first derivative sign chart, I've got a 0 here. My apologies if you can hear my 8-year-old screaming at his iPad right now in the background. I promise everybody's okay. Okay, first derivative sign chart, got a critical point at 0. If that's a max, that means that this is positive on this side, negative on this side. Increasing, decreasing. So we know where it's increasing or decreasing. We know where our relative extrema are. The next thing to look at is concavity. So if you're scrolling up to the box with the strategy, we just got through part E, and now we need to do F and G, inflection points and concavity. We need to look at the second derivative for the sake of concavity. So we're going to say, what makes this equal to 0? Well, that basically is just two different factors. What makes this factor equal to 0? Nothing. Just like we said before, there's nothing that you can raise e to a power and get 0. And so this is the one that's going to give us any potential inflection points right here. X squared is a half. So we're looking at positive or negative 1 over radical 2. And we're going to build a second derivative sign chart. Negative 1 over root 2, positive 1 over root 2. These are x values. These are second derivative signs. Now I'm going to think about this version, this factored version of my second derivative here. Let's see, where can I look at it? And we're thinking of this piece of it. When you take 2 times e to a power, that's always positive. So we really only have to consider whether this piece is positive or negative, and that will tell us if our entire second derivative is positive or negative. So I'm kind of just looking at this in here. All right, so if I plug in 0, it's going to be like 2 times 0 minus 1. That's negative. If I plug in some huge number, 2 times a million minus 2 times a million squared minus 1, positive. If I plug in negative a million, square it, you're still going to get 2 times a million minus 1, still positive. So what we figured out there is that we've got concave up, concave down, concave up. But again, don't fall into the trap of assuming that it's just going to look like this, because that's how polynomials work. That is not how exponentials usually work. So we've got inflection points at this positive and negative 1 over root 2. We know our concavity. We've got basically everything we need here. We have a function that's going to increase and then decrease, but it doesn't just increase and decrease because the concavity has to do this. So that means it kind of has to do this. It has to still be like going down on both ends. It can't turn around and go up, but it has to be concave up. Concave up, but still decreasing here. Concave up, but still increasing all the way through here. So we're going to have that type of shape. We also know we need a horizontal asymptote in both directions at the x-axis. So that's sort of piecing together what a picture of this might look like, right? All right, let's sketch a graph. We've got a y-intercept at 0, 1. Zero, 1 is also a max. And so I know my function's going to kind of do this. And then I know the inflection points are at 1 over root 2 and negative 1 over root 2. So that's not a place where it turns around and starts going up, but it's a place where it changes from concave down to concave up. And so here's what that's going to look like. I want it to be concave down all the way from here to here. Let me stop and make this a little prettier. Concave down all the way from here to here. And then at those points, it's going to turn to concave up. But it still has to keep decreasing. So don't be tempted to make it go up like that to make it concave up. It has to still be decreasing. So it's going to be sort of like this. And then we know we have a horizontal asymptote at the x-axis, so it's going to level off like that. My x-axis is not as straight as it could be, so it looks a little weird there, but you get the picture. And then same thing happening over here. Here's where the concavity changes. So this is concave up. It's going to level off at the x-axis. So then you can see here, like this is concave up, but this is concave down. And then this is concave up again. It's a very subtle difference because we can't actually change direction, but we are changing the concavity. And then once again, I encourage you to grab your calculator and graph this, or open up Desmos or something to look at a graph, and then you can see how all of these things kind of go together.